Kevin Ernst is a principal geotechnical engineer with Terracon Consultants and the Appalachian Regional Manager for them as well. He is a professional engineer who's been practicing since 1991 in Pennsylvania, Ohio, Kentucky, and West Virginia. He has extensive experience in steep slope technical projects in the region of West Virginia, including design of cut rock slopes reaching 300 feet in height. He served as consultant to numerous oil and gas and interstate pipeline companies. A graduate of Purdue University, Mr. Ernst holds a master's degree in civil engineering from the University of Rhode Island as well. He's a retired captain in the U.S. Naval Reserve and serves in the United States Navy in nuclear propulsion. So please join me in welcoming Kevin.
Thanks, Drew. Thanks for the opportunity to speak today. I'll try to keep us on track here because I know I'm the last bastion between the lunch and the break. So what I'd like to talk to today about my topic, the topic of the conference was risk. And there's a lot of discussion about installation of pipelines, carbon sequestration with new pipeline infrastructure. And when you look at this region, the Appalachian region, there is a lot of risk related to constructing in the shallow surficial geology. So I'll go ahead and get started. A little plug for the company. Terracon, we're a national firm since 1965. In the region here, we were previously H.C. Nutting Company. Been practicing granddaddy of geotech engineers since 1921, 5,000 employees, 150 offices. This is kind of a map that shows the major basins, and you can see that we're well positioned to support the oil and gas industry, especially here in the Appalachian Basin. A new acquisition, Skelly and Loy, Dan Davis, our BD leads, sitting over here in Pittsburgh. So we've got operations here in Pittsburgh, and just move on a little bit. I'm going to focus on, we support, provide services for geotechnical engineering, materials testing, environmental services. But today's discussion, I'm going to focus mainly on the geotechnical engineering aspects, specifically geohazards, because that relates significantly to issues of risk in construction of pipelines and midstream facilities in this region. So I'm going to talk about an innovative tool that Terracon has developed that it relies on public data, relies on our professional practitioners, our geologists and our engineers, our local knowledge, but takes a lot of existing data and makes it smart to help into planning and to also focusing where you need to focus your risk management. So I'll just kind of go through that. Next couple slides, just again, we support all services in the upstream, midstream, downstream realm. We'll focus more on the midstream. These are some of the project works that we've worked on. We've supported emergency response, geohazard evaluations, risk assessments related to high strain, developed by ILI data, et cetera. So just kind of see we've got services both here in eastern and western U.S. But let's go ahead and get started on geohazards. Geohazards result from natural processes of a geotechnical, geological, or hydrogeotechnical origin. We're going to kind of touch on all of them here. Mainly in this region, it's landslides and slope instability, rock falls, earth flows. There's issues here with settlement and karst, abandoned underground mines. That's a big issue here in this region, here in eastern Ohio. Fairly shallow mines that can be extreme risk to construction in the area. Seismic, ground motion, fault ruptures, largely seem to be more significant out in the western portions, but there are some significantly buried deep faults in our region. And then hydrotechnical relates to flooding, surface water, scour, et cetera. So I just wanted to kind of review, just a little show and tell on what these features look like, because as part of a project development or even installed systems, you want to be able to identify the features, and that's what you need professional assistant to take a look at to help guide that process. This is a typical landslide, rotational slip. You'll see it around here. It's developed by the loss of shear strength in the soil related to loading or high rainfall or poor water pressure development of the subsurface. And you can see the characteristic properties of it. Typically has a crown headscarp and a toe bulge. You can see as if you were constructing a pipeline through here or constructing a compressor station or another facility, that if you construct it along or near slopes, this can be a significant issue or a significant risk to your infrastructure. Other landslides would be rock falls. Again, rock falls can create issues with both in facilities, cuts. If you're designing cut slopes in your facilities, a lot of times you need to level out building pads, so you might have rock cuts, personnel hazards, hazards to your facilities. Mud flows or debris flows. Again, it's typically associated with a lot of groundwater or precipitation that initiates the landslide and results in a flow downslope. Creep movement, much more subtle. This is long-term. All the soils, gravity's constantly working on soil, so slopes around here are constantly moving around. So if you construct pipelines through these regions, you could have slow strains to your pipelines, depending on how they're oriented. And you want to be aware of that. So that situation you need to also be aware of and look for these characteristic features, in the pre-construction reviews. Some more show and tell. This is kind of an interesting slide, subsidence in terms of karst. Karst is commonly found in the limestone units, results in the groundwater. Basically, we had a lot of talk about carbonic acid, basically the rocks dissolving and creating voids, creating potential subsidence of the surface. So again, construction at near surface, and these features, you want to be aware of where these zones are so you can site your facilities properly. The other one, this is an interesting one, underground mines. This is an actual project I was involved with during construction of a pipeline where they're going through an area and the contractors actually came upon some sinkholes, which could be, so it basically results in typically room and pillar type mining where you have a collapse of the roof rock with subsidence on the surface, often shallow, more shallow based. Again, there's seismic hazards. Again, a lot more faults like this would be found more out west. So, but those are some of the other features. So, and hydrotechnical. So, I wanted to talk to you about an innovative approach. It's pretty much a standard approach to geohazard risk management. This chart, and we'll touch on each one of these different colored arrows here. The first step is really to identify it. That's kind of what I went and did the show and tell for, to kind of show you what these hazards look like. Because you have to identify them if you're going to be able to construct and build and operate within them. And so then the next thing is you typically do that through a desktop study and then a field reconnaissance. So I'll focus on that area. And mainly on the desktop study, on how we can take some of the existing data to support the desktop study level work. The next thing is to assess it, develop your risk profile. How much of a hazard is this, and how high of a risk? Is it a very, very strong risk, or is it more subtle where we can monitor it and take a look at it over the long term? And then mitigation, there's various ways to mitigate. I'll talk a little bit about some techniques to mitigate, lower your risk. But in some situations, you might be able to reroute, but other situations, you're going to have to build on that ground. There's only one way to get between point A and point B, and that's how you get there. So you have to identify mitigation methods, and then there's various ways to mitigate. And I'll give an example of some landslide mitigation, which is pretty applicable to this region. And then monitoring. There's monitoring. Monitoring can be used part of the assessment phase to kind of monitor it, like that creep I showed. You might be able to just monitor that for a period before it becomes excessive. That might create stress or strain on your systems. Or after post-construction, you're still constructing in a risky area. You may want to monitor it for the long term to set some action levels to see where you actually might have to implement a more rigorous mitigation. So let's just take a look at each one of these categories. Identification, desktop study. Typically, desktop studies, what we've done in our company is we've developed some GIS-based models that help us basically do these desktop studies from the old days. I used to spend, I did work with underground mines. I spent hours down in the DNR's map room pulling out maps, and I'd come in, and then the lead geologist would run upstairs and disappear for 3 hours, and there I am waiting for my map, and I had to go back to the office and then try to figure out where it, tape it up. I didn't have a light table, so I used to tape it up on the window. To see, to overlay it on my site to see where all these old mines and stuff were. But now we've got GIS, and a lot of this data is out there publicly. The state of Pennsylvania has significant data, state of Ohio, all the DOTs have data. So what we've done at Terracon is we've taken all that data public, and then we've overlaid our private data on it, which is all of our thousands of borehole logs that we do. We're a heavy geotechnical firm. Got a lot of information. So that's part of the desktop study. I'll go over kind of that process here. This is kind of like I said, the world of big data. This is old Stan Bollinger down in our Cincinnati office. Stan's, I think he's over 80, 85 now, and he's still working. He was our CAD guy that hand drew all of our boring log sticks. But this is the way they used to do it, right? You go into a big room and pull stuff out of your file cabinets and hope that the flooding of the basement didn't destroy all your records. So, but there we were now. But now here we are now. So here's what it looked like back at H.C. Nutting. This is a shot of Cincinnati at H.C. Nutting's pin map that showed all their project sites. That's greater Cincinnati right there. But here's what it looks like now in our GIS. We've got pins. We click on them. We've got all this data. You click one of those pins. You bring up the information, which all information is valuable, but it's only as good as if you can compile it and figure out what it's telling you. So what we've done is we've taken a lot of this public data. This is kind of the heart of the desktop model that can be implemented to kind of support your desktop study. Is the first graphic up here on the left is really kind of taking the download and clip the area of interest. That might be example of a section of a pipeline that's going to be constructed. Okay, and then we overlay. We've got elevation data from state LIDAR, various other sources, so we know what the ground elevations are. The state of Pennsylvania or state of Ohio or any state geologic survey has available mapping. We take all that available mapping, we overlay that in our GIS, then we start writing scripts. Okay. For example, I'll show you next is kind of like a landslide hazard model. Landslides aren't going to happen on flat ground, right? So it has to be on a slope. So that's why elevation data is important. Some geologic units, such as the Connemara around here in Pennsylvania, is very susceptible to landslide, just very weak shales and bedrocks. So we know we can characterize those, our professionals can characterize those and give those a level of risk. and then we kind of overlay that, run a logic, and we can develop a model. Okay, if the slope angle is over a certain degree, we have this type of bedrock unit. We can overlay the groundwater models. We can see where we can make modeling where the streams are undercutting the slopes, which might give you a higher hazard. And then from that, we can develop a level of risk. So, kind of as an example, everyone's probably pretty familiar around here with the Utica play, right? So this is kind of a map that shows where, this is the minerals we're going after, right? Oil, wet gas, dry gas. So, it's interesting to show when you look at, this is the Usgs's landslide susceptibility model or mapping. And the red is showing the area that has a very high incidence of landslides. Well, take a look at the zone we're in versus that play map that I just showed you. We're in a very, very risky area to develop oil and gas infrastructure. So we need to be very smart about it. So what we do, this for example for landslides, what we've done is, we've kind of taken the map. Okay, now you're zooming in there. Well, if you look at just the published data, you're going to say, well, there's no place to build out here. It's all red. What am I going to do? But then what we do is we take that information that I just said and apply the logic to it, the steepness of the slope, the bedrock type, the water, and then we're able to create a more precise risk model to kind of show where we think the areas that are going to be most susceptible to landslide are going to occur. This is a starting point. This is all done desktop level. So, so for example, this is kind of a zoom in of a section of pipeline that you might look at. And you can kind of see the pipeline going through there. And then what we've kind of done is we've broken it down to zones so we can start taking a look at certain zones of the pipeline where we predict that there might be a higher incidence of landslides. And that's where we can go out and start focusing our field recons and our reviews to help mitigate the risk. Another tool that's useful in desktop studies that's really becoming a quite useful tool is using LiDAR, light detection and ranging, basically from aerial overflights with leaves off. You can process the data, take out all the vegetation, and get really accurate maps of the surface. The surface of the ground, of which a trained eye can start picking out these landslide features that I illustrated in the features. So, this, for example, that's kind of a before and after of a major landslide slip. But a lot of those features could be seen in that first shot that I showed. So LiDAR's a tool can be used for desktop. They're different. It's not only landslides. There's a lot of state has karst mapping, so you can see where your facility, your pipeline is going to be positioned over ground that might have a potential to karst sinkholes. A couple of years back, you've probably heard in the news, the Corvette Museum, that was right over a huge sinkhole. Quite interesting. So it's good to go into it with eyes wide open, not necessarily after the fact, where you're prone. Abandoned mines. This is again a pipeline project where the pipeline was going over areas of shallow underground mines. So as part of the planning, you can plan. If you can't reroute, what can you do to mitigate that? Grouting program, monitoring programs, based on engineering assessments. So again. There's a lot of, active mineral plants. So there's just a ton of different layers in there that we can look at and overlay and kind of develop the risk. So in the end game, you take all this data and you synthesize it and you kind of break it down and make it user-friendly. You kind of break it down into units and start taking a look at certain areas where you're more concerned than others, and then you can start your discussions on risk mitigation. And again, risk mitigation, it all comes down to cost, right? So You have to be aware what if you can mitigate your risk by reroute or another method, or certain methods. If we go a slightly different route, are we going to have a lower risk that we can use a less expensive mitigation measure? So it's really good for planning, but it's also good for the system is also good. We've used it for clients to also look at from an integrity basis. After an operating pipelines that have been in place for 50, 100, well, some up to 100 years, but 40, 50 years now that really didn't have this level of detail to go back and quickly analyze that. And there's a lot more technology with your inline strain measurements. You can start. A lot of the clients we work for are giving us identifying issues in their strain readings, and then coming back to us, we can overlay it on our model as a starting point to see what the issues are, and then actually go into the field and actually do physical assessments of what the issues are. Are we seeing that high strain because it's in a landslide, or is that more of a construction feature that's being seen? So. A lot of our applications, again, we're away from paper reports anymore. And the best way to synthesize this is in a web portal. And so that same model, that same engine that we've built as the engineer, the client gets it. So he or she can basically turn those layers on and off. They can look at areas of high risk, low risk, where's the karst, where are the landslides, whatever feature they want. We can take all their existing maintenance data and put it in. Anything that you can put spatially, geographically, can go into these models. So pretty powerful tools, relatively inexpensive and to develop, and relatively gives you a lot of good information, especially in the planning phases. So again, the end game is you want to develop a relative risk. So a lot of it's related to the risk profile that the client is, really the owner is willing to accept for their project. So we work with the owners to kind of develop their risk profiles and kind of rate the sections, and then that can help guide their either asset management if they're doing asset management, or can also help guide the planning. I mean, if we're going to be developing much more pipelines, which I think it sounds like it's happening if we're going to a carbon sequestration, these models can be very, very effective in helping understand the risk in the pre-design work. So that's the main focus I wanted to discuss today, but I'll go over some of the other things that we do as engineers. Field observation. It's great to have all these computer models and stuff, but do you really believe them that much? The only way to do it is to ground truth them. So we've done helicopter overflights. We've got field crews that are trained geologists that go out in the field looking for these hazards. We're going to go validate that model. If we're seeing high landslide susceptibility in a certain region or a certain zone in our mapping, we're heading back there to take a look to see what those features, what we're really seeing. So other things, again, field recon, aerial overflights on the ground. There's nothing like boots on the ground. That's the best way to do it with a trained eye. Depth of cover for the pipes in the hydrotechnical, very important. We need to understand if it's an existing pipe, how deep it's buried, and so we can analyze the scour with our modeling and erosional features, surveys of streams. So that's the identification. Now this is more kind of going into the assessment phase. Okay, now let's say we're going to build something. Well, or we've got an existing landslide that's encroaching on a pipeline. I'll give an example of a remediation that we did, a mitigation. But there's several tools that are in our toolbox to go out and assess them. And typically, one of them, the most common practice is, nothing nothing as good as getting the ground truth, right? And the only way you're going to get the ground truth is by drilling it, right? You're never going to, you can model, you can test, you can think the oil's there, but until you drill it, you don't know. So it's the same thing. We go do a subsurface exploration to understand the characteristics of the subsurface. What's the strength of the rock? Where's the groundwater? How deep? What kind of issues are we seeing? So, that's part of the assessment. Again, drilling, that's a good pipeline. I like that photo there. It's a good pipeline photo. We were drilling over in eastern Ohio. One of our crews.
I like that photo.
Yeah, it's beautiful. Other assessment tools, geophysical. We have geophysicists, we can do, we've been pretty successful using electromagnetic surveys to help identify top of bedrock, underground, karst features, voids, things like that. There's various geophysical methods that can be brought to bear. So as part of the assessment, we have a lot of tools in our toolbox, and we pick the most appropriate tools, of which geophysical may be the case. We bring those samples back to the laboratory and we test them, because if we're gonna go into a mitigation, we need to effectively characterize the soil and bedrock, the strength of it, the permeability. These are some of the tests that we do. A lot of it you can get from very simple classification tests. Understand, what they call Atterberg limits, to understand the plasticity, gradations, and basically characterize the soil, and then we know. But in certain cases, especially in slope stability issues where you have landslides, you really need to do physical properties testing and get some really high quality shear strength data, so you can effectively design a fix to the problem. Again, instrumentation. Part of the assessment, like I was talking a little bit about that creep, the soil creep. Maybe the assessment is just to monitor it long term, to see what's the rate of movement. Is it moving fast? Is it moving slow? Does it look like it's going to fail imminently? So we have different tools. We can install what they call slope inclinometers, which is just a borehole application. It just has channels that you run a device down, and it just measures. You go back periodically and it just measures the deformation of the pipe, so you can kind of see where the ground might be moving. Extensiometers, you can put them in the ground and measure the movement of the ground surface. So there's different monitoring applications. And finally, in mitigation, there's various mitigation methods. GSI over here can talk about the soil nailing. They basically can, there's different methods. The top left is really a lot of landslides, and you can basically excavate and reconstruct and get drains and reconstruct it. It's an earthwork option, but it's not feasible on all projects. And sometimes the slips are so big, you just want to need to protect the asset. So you might put a pile and lagging wall, and I'll give an example of a project like that. Soil nailing or rock anchors, rock bolts, depending on the application, to protect, to mitigate zones of problems. And mainly I'm kind of focusing on landslides right now, but there's different forms of mitigation. This is just kind of a general mitigation approach. I mean, like I talked about, the easiest thing for example, a pipeline or a facility, based on your desktops and your field recons and your assessments, you might just want to avoid it if you can reroute. But a lot of times you can't, like I talked about. So there might be situations where you can use temporary strain relief. For example, longwall mining. There's a lot of I was on a project where the mine was, longwall mining is where if you're not familiar with it, is where you basically just mill out. You're milling out at the coal seam, and then the roof rock collapses behind the milling operation. And what it ends up doing is the entire rock soil profile subsides over a relatively short period of time. But you can't be installing facilities in an area of longwall mining. So you might just leave the pipe uncovered and let the ground subside, and then go ahead and complete. And a lot of times with landslides, you give it temporary relief as a temporary mitigation in the time that before you come back and implement the final fix. It's good to know pipe isolation, the depth of rock. A lot of the slope movement around here is it slides on the top of rock. And if the top of rock is relatively shallow, you may do your design to actually notch that pipeline deeper into the rock. So if you do have creep movement, for example, that the soil is going to creep right over the top of the rock, it's not going to affect your pipeline because it's socketed into the firm material that's not moving. You've got various backfills or wraps you can put around, for example, pipelines to mitigate the friction and stress on it. For earthwork fixes, like I said, some of the landslides you can just excavate out and replace. Drains. Your pipeline design there's various features that you need to control with vegetation. You can slope reinforcement, drains, breakers, things like that. You can flatten areas during your restoration, but the biggest key is drainage. Bottom line, that's the biggest cause of the issues around here. You've gotta work the drainage into your construction and your post-construction design to make sure that you're not going to have the water destabilizing the slope after you've restored it. So, and then you've got the final one, and at the bottom is really more of a geostructural. You're back to the soil nailing or rock anchors, or retaining walls or pile and lagging. So I'll finish it up with just an example of a pile and lagging mitigation. This is an example of a landslide where the 20-inch gas line kind of runs right along the slope, and right below the pipeline, a rotational landslide has started to develop. The first thing is we've gone out, we've collected that drilling and laboratory dating. We might have done some geophysical on it, and then we go into an engineering analysis. This example is for a design of a pile and lagging wall. The fix was they decided to protect the asset, so put a pile and lagging wall parallel to that 20-inch gas pipe along this area that was identified that was having a landslide. So we do engineering calculations with, I won't get into the details of that, but we basically do calculations and size the strength and the size of the pile that we need to do. And I'll show you what a soldier pile, if you're not familiar with them. So this is, let me keep going here. So let's just kind of show calculations. This is the next phase of it is an engineering design. You're gonna after you characterize it and kind of do your engineering analysis and design, you need to get it into a drawing so that your contractor can install it properly and mitigate your risk. So this is an example of it. The plan view is on the left. You can kind of see there's a elevation view of the profile of the pile and lagging wall. And then this is a cross section of it. So basically what you do is you create a bench on the hillside. You go in with an augering machine, drill a shaft, and then you drop a steel beam in it and concrete it in, and then basically place either concrete or sometimes wooden lagging panels and basically reestablish the grade and protect the pipeline. So here's some construction photos that kind of give you a flavor. The crew might mobilize to the site. They're preparing the site. They're cutting out a bench there to work on. You can kind of see the pipe is previously on the right on the photo. The pipe's previously been exposed there because it was uncovered. So if the landslide kept moving, it wouldn't additionally stress the pipe. This is a picture of the drilled shaft soldier pile installation. Again, you can kind of see with a drilling augering machine, they drilled boreholes down to the design depth, typically socketed into the bedrock below the zone that's slipping, and insert a appropriately designed steel beam. Typically, there's 6 to 8 feet spacing on these things. Might be typical, depending on the loading. There's a photo of the lagging installation. And backfill, back behind the wall, it's important to make sure you have good drainage back there before you backfill it, so that any water that's coming down slope and is behind the wall is drained out. So you're lowering the loading. Hydrostatic pressure is a lot of pressure. So you want to, again, water's the culprit. If you remember anything from this talk, is water's the culprit with the landslides. So. And then there's kind of the finished project, little seed, little turf reinforcement, and your pipeline should be protected. So, and there's, that's just an example of a mitigation. There's all different types. If you're going to underground mines, it might be that you just, again, monitor it with strain gauges for a while. Develop a grouting program to fill those. A lot of them, if they're shallow, you can just excavate them out. If they're very shallow, just when you're constructing, excavating out. So the last thing I wanted to talk about is basically a monitoring. For example, after that wall was built, you might want to, depending on your design, you might have inclinometers there to measure for future movements. Maybe upstream, maybe if it's in a landslide prone zone, you might put an inclinometer. Just you're suspecting that other portions adjacent might have a similar issue, because you're just focusing on an existing slide, but you think you're going through a slide prone area. You might install inclinometers as a proactive measuring. Strain gauges, piezometers. Piezometers are like wells to measure groundwater, again, to get an understanding of what's going on with the project. So. A lot of times this can be implemented as a risk mitigation measure that's maybe the least expensive option if you're in a risk zone, but it's not deemed to be a high risk. So and a lot of companies do this. Let's monitor it till it gets to an action level, and then we can kind of budget. As part of our integrity and our monitoring program, we can use those resources and budget them for further on out as we kind of monitor as things move along. So, any questions that I can answer? Thanks for your attention. Did I keep us on schedule, or am I a little bit off?
Yeah, we're good.
Okay.
We have time.
Yeah. Any questions I can answer? Yeah. Go ahead, Dave.
So. The decision to go deeper into the rock to ensure that you're mitigating the risk of that slide, is that a collaborative effort? I mean, that's a very expensive thing. So before anybody does that, that would be a customer decision.
Yes, exactly. I mean, and that's why you could, if you can get an understanding of your depth of bedrock and your risk during the pre-design, is probably the best time to make those decisions.
So that you can make sure that they
Right.
see these upfront costs.
Right, and a lot of times it's field too, because we're out in the field watching these going in, and if we're going through a zone, because a lot of the you're going miles and miles with these pipelines. You can't characterize every square foot of that. So the idea is you have trained with your teams, like we did this, for example, a good example is we did it out in Virginia and some of the karst regions. One of the pipeline companies actually hired us to have our trained geologist out to identify karst hazards as they're digging. So that, I think maybe if you're expecting that, maybe that's best used as a field contingency. That you've got some budget to deepen it in. And a lot of these bedrocks where you're having the problems, they're soft rock. And so it's not like you have to go and drill and blast these. A lot of them are just softer shales that you could still excavate relatively simply with an excavator with some rock teeth on it. You know what I mean? So we're not talking hard rock. Most of this To take it deeper in the rock is going to be soft rock type excavations where, right, instead of putting it at 3 feet, you're putting it at 6. Now you're socketing it into the rock.
I only had one other question.
Yeah, Dave.
Only one.
Yeah.
One of the last slides, well,
Yeah.
the finished product of the,
Pile lagging wall? Yeah.
there was a guardrail at the top of the wall, but nobody's driving down through there. Is that
Well, it might have been along an existing access road. So it would all be dependent on what the requirements of the project are and what the owner is, because a lot of these pipelines they'll go down on people's ATV trails and stuff like that. So the landowner, and it might even be a negotiation with the landowner,
Right, okay.
so it's
unnecessary.
yeah, no, it's not something that you automatically put into each design. It's case by what the owner wants. Yep. Any other questions I can address? I appreciate your time. Thank you very much.